A rare visitor from deep space is flying through our solar system. The object, now officially named 3Y Atlas, has astronomers spotting another mysterious interstellar visitor racing through space. NASA's recent data has revealed anomalous features that have sparked intense debate over its true nature. Some scientists fear the possibilities this mysterious visitor presents, suggesting it could be more than a mere comet or asteroid, perhaps even a disguised alien ship. This revelation has generated both excitement and apprehension within the scientific community as we strive to understand its origin and purpose. The breaking discovery. The initial detection of 3Y Atlas occurred in early 2025 by the Atlas Survey System, an automated telescope array designed to spot near-Earth and interstellar objects. Astronomers were immediately intrigued by the object's extraordinary velocity and hyperbolic trajectory that clearly indicated it was not gravitationally bound to our solar system. Dr. Larry Deneau, lead scientist for the Atlas project, confirmed the object's unique path and immediately alerted observatories worldwide to begin tracking this unprecedented visitor. The breaking revelation that 3I Atlas was significantly larger and faster than previous interstellar objects reignited debates about the prevalence of such cosmic travelers. The discovery highlighted the increasing sensitivity of modern astronomical detection tools and emphasized the critical importance of global coordination in tracking these extraordinarily rare cosmic interlopers. Initial observations revealed unusual characteristics that defied conventional explanations for natural interstellar objects. The object's behavior patterns suggested it might possess properties unlike anything previously encountered in our solar system. This discovery marked a pivotal moment in interstellar object research, forcing scientists to reconsider fundamental assumptions about what travels through the void between stars. The discovery story. Following the initial detection, astronomers rapidly organized international efforts to gather comprehensive observational data on 3Y Atlas during its brief passage through our solar system. Utilizing powerful instruments including the Hubble Space Telescope and sophisticated ground-based observatories, they systematically confirmed the object's size, composition, and increasingly unusual behavioral characteristics. The European Southern Observatory contributed crucial spectral data revealing complex surface features that appeared inconsistent with known cometary or asteroidal bodies. Dr. Michelle Bannister from the University of Canterbury discussed the significant challenges involved in imaging such a fast-moving, distant object while maintaining the precision required for detailed analysis. The collaborative international effort underscored both the urgency and scientific significance of capturing comprehensive models of 3 and Atlas during its fleeting passage through our cosmic neighborhood. Teams worked around the clock to coordinate observations across multiple time zones and hemispheres. The unprecedented level of cooperation demonstrated the scientific community's recognition that this visitor represented something truly extraordinary. Each new observation added pieces to a puzzle that seemed to defy conventional understanding of interstellar objects and their expected properties. A stranger in our midst. 3I Atlas exhibits characteristics unlike any object previously observed in our solar system or beyond. Recent measurements indicate it possesses unusually high reflectivity and metallic surface characteristics that fundamentally defy typical comet or asteroid classifications used by astronomers. Dr. Alan Fitzsimmons from Queen's University Belfast analyzed extensive telescope data, highlighting the strange spectral signatures indicative of advanced materials, rather than natural rocky or icy compositions. Traveling at nearly 60 kilometers per second, the object exhibits unexpected trajectory modifications that some researchers interpret as evidence of artificial propulsion systems. These remarkable anomalies have led a growing number of scientists to propose that 3Y Atlas may represent a technological artifact, possibly an extraterrestrial probe deliberately sent to observe our planetary system. Continued observations aim to definitively determine whether its behaviors represent unknown natural phenomena or constitute evidence of intelligent design and construction. The object's surface appears remarkably smooth and uniform, lacking the typical irregular features expected from natural cosmic debris. Its thermal emissions follow patterns that suggest internal heat sources rather than simple solar heating. These discoveries have fundamentally challenged existing models of what interstellar objects should look like and how they should behave. The predecessors. The previous two confirmed interstellar visitors, known as 1I/Oumuamua discovered back in 2017, and 2I/Borisov detected in 2019, provide crucial context for understanding 3I/Atlas. Yet, none of these objects actually share its peculiar characteristics. Oumuamua, for instance, initially baffled scientists with its really unusual cigar-like shape and that completely unexplained non-gravitational acceleration, which honestly just defied conventional physics. In stark contrast, 2I/Borisov displayed classic cometary behavior, showing typical outgassing patterns and developing a visible tail, just as you'd expect from natural objects. 3I/Atlas, though, with its massive size and highly reflective surface properties, fundamentally challenges the notion that interstellar objects always conform to previously known natural archetypes. The growing dataset from these three dramatically different visitors is systematically reshaping our understanding of what might actually be actively traversing our galaxy. Each visitor has contributed unique insights while, at the same time, raising increasingly complex questions about the diversity of objects traveling between star systems. The progression from Oumuamua's mysteries to 3I/Atlas's apparent technological signatures really suggests an escalating complexity that, well, demands serious reconsideration of our assumptions about interstellar space and its contents. The Cosmic Journey. The cosmic journey undertaken by 3I/Atlas spans potentially billions of years, originating from some unknown star system located far beyond the boundaries of our solar neighborhood. Dr. Davide Farnochia from NASA's Jet Propulsion Laboratory explains that the object's estimated age and remarkable velocity suggest it has successfully survived countless cosmic events, stellar encounters, and gravitational interactions during its extended voyage. Its calculated trajectory indicates a passage through the harsh environment of interstellar space for, potentially over 1 billion years, making it an ancient relic from the early epochs of galactic formation. Sophisticated spacecraft instruments have detected faint emissions, possibly linked to its primordial origin, which offers researchers a unique observational window into materials and processes from beyond our solar system. Understanding this extraordinary journey provides crucial insights into the fundamental processes shaping galactic evolution and the distribution of matter throughout cosmic history. The object's apparent structural integrity after such an immense voyage raises some pretty profound questions about its composition and construction. Natural objects typically show significant degradation after extended exposure to cosmic radiation and micrometeorite bombardment, yet 3I/Atlas appears honestly remarkably well preserved. A scientific goldmine. The discovery of 3I/Atlas represents without a doubt an unprecedented scientific opportunity, with an international array of telescopes and observatories now focused on capturing every possible detail during its passage. Scientific teams from NASA, ESA, and numerous other agencies are collaborating intensively to analyze spectral data, refine orbital models, and systematically search for evidence of non-natural phenomena. Dr. Sarah Seeger from the Massachusetts Institute of Technology emphasizes the extraordinary opportunities this visitor presents for studying interstellar chemistry, exotic materials, and potential technological signatures. The comprehensive data collection effort could, potentially unlock fundamental secrets about planetary formation processes in distant star systems and provide insights into the prevalence of advanced technology beyond our solar system. Each observation is carefully coordinated and scheduled to maximize scientific return during the object's limited time within optimal viewing range. The international cooperation on this project demonstrates unprecedented levels of coordination among research institutions that are typically quite competitive. Advanced imaging techniques are revealing surface details that really challenge our conventional understanding of natural space objects. Spectroscopic analysis has detected unusual emission lines that don't match any known natural materials, fueling speculation about artificial construction and exotic engineering materials. Unanswered questions. Despite extensive international study efforts, fundamental questions about 3I/Atlas remain frustratingly unanswered, leaving scientists divided about its true nature. Dr. Avi Loeb of Harvard University points out that certain observed behaviors definitely defy all known natural processes, including, unexplained acceleration patterns and highly unusual surface reflectivity characteristics. The object's true internal composition, structural configuration, and ultimate origin remain completely elusive despite intensive investigation. Competing hypotheses range from exotic natural cometary remnants to sophisticated artificial probes, potentially sent by extraterrestrial intelligence for reconnaissance purposes. Ongoing research efforts focus intensively on resolving these mounting mysteries, bolstered by significant advances in instrumentation and increasingly sophisticated observational techniques. The international scientific community remains fundamentally divided, carefully balancing healthy skepticism with genuinely open-minded inquiry as new data continues emerging. Some researchers argue for natural explanations involving unknown physics or exotic materials, while others increasingly favor artificial origin theories. The lack of definitive answers has created intense debates within astronomy journals and conferences. Each new observation seems to deepen rather than resolve the central mystery surrounding this enigmatic visitor from interstellar space. The alien question. The possibility that 3I/Atlas represents alien technology has moved from fringe speculation to serious scientific consideration among mainstream researchers studying its anomalous properties. Evidence supporting artificial origin theories includes the object's unusual mathematical heat emission patterns, sophisticated trajectory adjustments, and surface materials that appear inconsistent with natural formation processes. Dr. Seth Shostak from the SETI Institute reports that thermal emissions follow prime number sequences that are extremely unlikely to arise naturally and may represent deliberate signals or encoded information. This finding significantly strengthens the possibility that the object functions as part of a broader network of interstellar probes, communicating through universal mathematical codes that any technological civilization would recognize. The hypothesis suggests systematic interstellar exploration conducted by advanced civilizations using sophisticated reconnaissance technology designed to remain undetected until closely observed. Understanding these potential signals could fundamentally transform our approach to searching for extraterrestrial intelligence and establish first contact protocols. The implications extend far beyond academic interest, potentially representing humanity's first confirmed encounter with technology from another world. Such a discovery would necessitate careful consideration of response protocols and international cooperation in managing potential contact scenarios. Observing the visitor. The global astronomical community has mobilized unprecedented resources to observe 3I/Atlas, coordinating space-based telescopes, ground observatories, and advanced detection systems worldwide. Dr. Nancy Grace Roman's space telescope operations have been specially configured to track the object's trajectory and capture high-resolution images during optimal viewing windows. The Vera Rubin Observatory contributes continuous monitoring capabilities, while radio telescope arrays search for potential technological emissions or communication signals. Dr. Michelle Bannister from the University of Canterbury coordinates international observation schedules to ensure maximum coverage as the object traverses different regions of sky visibility. Advanced spectroscopic analysis reveals surface features that appear artificially smooth and uniform, lacking the typical irregularities expected from natural cosmic debris shaped by millions of years of space weathering. Thermal imaging detects internal heat sources that suggest active systems rather than passive solar heating patterns typical of natural objects. The coordination represents the largest international scientific collaboration in astronomical history, with researchers sharing data in real time across continents. Each observation window provides crucial data that may determine whether humanity faces a natural phenomenon or evidence of extraterrestrial technology visiting our solar system. Dawn of a new era. The implications of 3I/Atlas extend far beyond simple astronomical curiosity, potentially marking the dawn of a new era in humanity's understanding of our cosmic environment. Dr. Michio Kaku from City College of New York suggests that whether this object proves natural or artificial, it fundamentally challenges our assumptions about life, intelligence, and technology in the universe. The systematic study of 3I/Atlas has already driven innovations in observational technology, international cooperation protocols, and theoretical frameworks for understanding interstellar phenomena. These technological and methodological advances position humanity to better detect, analyze, and potentially interact with future cosmic visitors. The growing frequency of interstellar object detections suggests we may be entering an era of regular contact with materials and possibly intelligence from beyond our solar system. Future missions may attempt direct rendezvous with similar objects to conduct detailed analysis impossible from Earth-based observations. The scientific community recognizes that 3I/Atlas represents either an extraordinary natural phenomenon or humanity's first confirmed encounter with extraterrestrial technology. Either conclusion would fundamentally alter our understanding of our place in the cosmos and our readiness to engage with a potentially populated galaxy. The ongoing study of 3I/Atlas continues to challenge everything we thought we knew about interstellar visitors and our place in the cosmic community. Whether this mysterious object represents advanced alien technology or an exotic natural phenomenon, its discovery has already transformed our approach to studying the universe around us. As observations continue and data accumulates, humanity stands at the threshold of potentially world-changing revelations. Stay with Stellar Tech for continued coverage of this developing story that may forever change our understanding of life beyond Earth. What if the Big Bang wasn't the beginning but a rebirth? What if our entire 93 billion light-year observable universe is just a single object inside a much larger, older cosmos? This isn't science fiction, it's a possibility being explored by theoretical physicists, challenging our most fundamental understanding of existence. The clues might be hidden in plain sight, in the behavior of black holes and the baffling arrangement of the most distant galaxies spotted by the JWST. Let's explore this mind-bending possibility together. The standard Big Bang model. So, how did we arrive at our current picture of the universe? The story most of us know is the standard model of cosmology, first mathematically conceptualized by the Belgian priest and physicist Georges Lemaitre in 1927. It states that our universe exploded into being 13.8 billion years ago from a point of extreme density. From this intensely hot state, space itself began to expand. Over billions of years, gravity sculpted this expanding cosmos, pulling matter together to form the vast, web-like structure of galaxies we observe today. This model is incredibly successful. It explains the faint afterglow of the Big Bang, the cosmic microwave background, and it accounts for the accelerating expansion of the universe. This acceleration, confirmed in 1998, is often attributed to dark energy, which makes up about 68% of the universe. When combined with dark matter, at around 27%, it appears 95% of our cosmos is made of stuff we can't see or understand. This means that all the stars, planets, and galaxies we can observe make up a mere 5% of reality. The bottom line is the standard model, for all its successes, leaves us with the biggest questions in science completely unanswered. The black hole universe theory. What if there's a more elegant explanation? One that doesn't require inventing new particles or mysterious forces. A radical alternative, championed by physicist Nikodem Poplawski, proposes that our universe was born inside a black hole within a much larger parent universe. This idea flips our perspective on cosmic origins entirely. Instead of a singularity appearing from nothing, the theory suggests a physical process, the gravitational collapse of matter in a parent universe. Think of it like a star many times the mass of our sun collapsing to form a black hole, but on a cosmic scale. In this model, what we perceive as the Big Bang was actually the moment our universe formed inside that parent black hole. This framework elegantly resolves the issue of what came before the Big Bang, as the parent universe provides a clear preceding state. This cyclical model redefines our cosmic address, demoting our entire universe from everything that is to just one bubble in a potentially infinite cosmic foam. It also provides a physical source for the energy and matter in our universe, sourcing it directly from a pre-existing parent cosmos. In essence, the matter that makes up you, me, and the stars didn't appear from nothing, but was recycled from a previous cosmic iteration. Quantum mechanics and degeneracy pressure. Here's where things get really interesting, and it hinges on a core principle of quantum mechanics. Have you ever wondered what stops a dead star from collapsing forever? The answer lies in a rule established by the brilliant Austrian physicist Wolfgang Pauli. His exclusion principle states that identical particles, like electrons, cannot occupy the exact same quantum state at the same time. When gravity tries to crush matter into an incredibly small space, this principle creates a powerful outward push known as degeneracy pressure. The more you squeeze, the harder the particles push back. This is the force that supports white dwarfs against collapse, where matter is packed to a density of over 1 million kilograms per cubic centimeter. In even more extreme objects like neutron stars, the pressure is even greater, holding up against densities of over 100 trillion kilograms per cubic centimeter. This pressure is fundamentally different from thermal pressure, which supports a star like our Sun, as it doesn't depend on temperature at all. Proponents of the black hole universe theory argue that this same quantum pressure could operate on the scale of an entire collapsing universe, offering a mechanism to avoid the infinite singularity. The bounce mechanism. So, if a universe collapses, what happens when this quantum pressure kicks in? Instead of crushing down to an infinite point, a singularity where physics breaks down, the collapse could halt and rebound. This is the Big Bounce, a concept heavily explored in loop quantum cosmology by physicists like Martin Bojewald. In this scenario, as the matter of a parent universe collapses, it approaches the theoretical maximum density allowed by physics, known as the Planck density, which is about 5.1 times 10 to the 96th kilograms per cubic meter. At this point, quantum gravity effects become so powerful they overwhelm everything else. This force stops the collapse in its tracks and triggers a massive explosive rebound. This rebound event would be incredibly brief but unfathomably violent, essentially resetting the cosmic clock for the new universe. To any observer inside this newly expanding region, that rebound would look and feel exactly like a Big Bang, while potentially preserving information from the prior cosmic cycle. This bounce also offers a potential solution to the black hole information loss paradox, a major conflict between general relativity and quantum mechanics. The paradox questions what happens to the information about matter that falls into a black hole if the black hole evaporates. A bounce mechanism suggests this information isn't destroyed, but is instead carried through the rebound event into the new universe, preserving the fundamental laws of physics. Evidence from early galaxies. This might all sound like fascinating speculation, but where's the evidence? It might be hiding in the deepest images of our universe captured by the James Webb Space Telescope. According to the Standard Model, galaxies should build up gradually. Yet JWST is finding galaxies that are bafflingly massive and mature. For instance, the GLASS JWST Early Release Science Program, involving astronomers like Rohan Naidu, has identified galaxies like GLASS Z12 at a redshift of 12, meaning we see them as they were just 350 million years after the Big Bang. These galaxies are already 1 billion times the mass of our Sun, far larger than our models predicted was possible so early on. Furthermore, these ancient galaxies appear to host supermassive black holes that are millions of times the Sun's mass, a phenomenon that standard models struggle to explain so soon after the Big Bang. The Big Bounce model, however, offers a potential explanation, suggesting these black holes could be relics that survived from the previous cosmic era, acting as gravitational seeds. Galaxy rotation mystery. Now for another cosmic puzzle that might point to the same conclusion. In a random and uniform universe, you would expect galaxies to be spinning in all different directions, with a roughly 50-50 split between clockwise and counterclockwise rotations. But that's not what we see. A 2020 study analyzing over 200,000 spiral galaxies, led by computational astronomer Lior Shamir, found a significant imbalance. There appears to be a preferred direction of spin, and alignment across vast stretches of the cosmos. The statistical probability of this asymmetry happening by chance is less than 1 in a billion. This unexpected alignment, observed across a scale of billions of light-years, implies that processes during the formation of the universe were not as random as we thought. This large-scale pattern challenges the long-held assumption that the universe is the same in all directions, a principle that underpins virtually all of our cosmological calculations. This isn't a small, localized effect. The pattern of this cosmic spin is coherent across billions of light-years. Shamir's analysis shows the distribution of spin directions fits a dipolar pattern, meaning it has a distinct north and south pole just like a spinning magnet or planet. Such a large-scale coherent structure is extremely difficult to generate after the Big Bang and points instead to a fundamental property imprinted on the universe at its very creation. Schwarzschild cosmology. So, this idea of a universe inside a black hole isn't, entirely new. It actually falls under a concept known as Schwarzschild cosmology. The name comes from Karl Schwarzschild, who, way back in 1916, found the first exact solution to Einstein's field equations, describing the space-time around a spherical mass, what we now call a black hole. The model suggests that the observable universe is the interior of a black hole existing within a larger parent universe. From our perspective, the Big Bang was the formation of this black hole, and from the outside, our entire cosmos would just look like a regular black hole. The size of this black hole's event horizon is defined by the Schwarzschild radius, and for a universe with the mass of ours, this radius is, interestingly, remarkably close to the radius of our observable universe. Mathematically, the singularity at the beginning of our universe is similar to the singularity at the center of a Schwarzschild black hole. The edge of our observable universe, a sphere with a diameter of 93 billion light-years, acts much like a black hole's event horizon, a boundary from which light cannot escape to an outside observer. Black holes as universe creators. Let's take this idea to its logical conclusion. If our universe was born inside a black hole, what does that imply about the estimated 100 million stellar mass black holes in our own galaxy? It suggests that each and every one could be a gateway, a seed for a new baby universe. This paints a picture of a vast cosmic ecosystem, a multiverse where universes are constantly being born. This concept, known as cosmic natural selection and explored by physicist Lee Smolin, could even offer an explanation for the fine-tuning problem, the mystery of why the fundamental constants of physics are so perfectly set for life. If universes are constantly being created, then perhaps only those whose physical laws allow for the creation of stable black holes can themselves reproduce, leading to a multiverse dominated by life-friendly universes. This theory proposes that our universe is so adept at creating black holes precisely because it was born from one, continuing an unending cosmic lineage. Smolin's theory suggests that the physical constants, like the strength of gravity or the mass of an electron, could slightly mutate with each new universe born from a bounce. Universes with constants that are better at producing black holes will have more offspring, and over countless generations these properties will become dominant. This makes the fine-tuning of our universe for life not a lucky accident but a predictable outcome of cosmic evolution on an unimaginable scale. Torsion and space-time twisting. For a universe to bounce instead of collapsing into a singularity, you need a powerful repulsive force at extreme densities. One candidate for this force comes from an extension of general relativity known as Einstein-Cartan theory. The mathematics behind this were developed in the 1920s by the brilliant French mathematician Élie Cartan. This theory incorporates a property of space-time called torsion, which accounts for the intrinsic spin of fundamental particles. This spin is a fundamental quantum property like mass or charge that gives particles an inherent angular momentum. In standard general relativity, space-time can bend, but it cannot twist, making the inclusion of torsion a significant modification needed for this theory to work. According to physicists like Nikodem Poplawski, at the densities found inside a black hole, the interaction between torsion and the spin of particles would create a powerful repulsive force. This torsion-induced bounce would be the mechanism that creates a new universe inside every black hole, making them not just cosmic destroyers but creators. Cosmic anisotropy. The evidence for a preferred direction in galaxy spins points to a concept called cosmic anisotropy, the idea that the universe is not the same in all directions. This directly challenges the cosmological principle, a foundational assumption in modern cosmology. This isn't just about galaxy spins. Anomalies in the cosmic microwave background radiation, first noted in data from the WMAP satellite and later confirmed by the Planck satellite, also suggest a large-scale alignment. Physicist João Magueijo famously dubbed this the axis of evil because it aligned with our solar system's plane, a result so strange it had to be a mistake, except it kept showing up with a statistical probability of being random at less than 0.1%. These anomalies, once dismissed as statistical flukes or errors in measurement, are now forcing a re-evaluation of fundamental assumptions, which is exactly how science progresses. The cosmological principle of isotropy has been a cornerstone of cosmology for nearly a century, so challenging it is met with significant scientific skepticism. However, as observational data from projects like the Sloan Digital Sky Survey and the Planck satellite becomes more precise, these persistent anomalies are becoming harder to ignore. If the universe truly does have a preferred direction, it would force us to rewrite our most basic models, and would strongly imply an origin story that involves rotation, just as the black hole universe theory predicts. From the impossible galaxies seen by JWST to the mysterious alignment of galactic spins, we are faced with observations that don't quite fit our standard story of the cosmos. The idea that our universe is inside a black hole, born from a cosmic bounce, offers a potential framework to explain these anomalies without inventing new physics. It suggests we might be part of an endless cycle of creation. What do you think? Are we living inside a black hole? Let me know your thoughts in the comments below. Don't forget to like, subscribe, and hit the bell icon. Thank you for watching Stellar Tech. On August 6, 2025, the James Webb Space Telescope slammed into emergency mode to capture an object that really, honestly, shouldn't exist. Astronomers, including the Pan-STARRS team in Hawaii, expected a dying ball of ice. Instead, Webb's new data on the interstellar comet 3I Atlas just confirmed a chemical nightmare. This visitor isn't just unusual, it's breaking every rule in the book, and the deeper the data goes, the more unthinkable the questions get. Let's explore this together. Emergency override, Webb's unprecedented response. What does it take to stop the world's most powerful space telescope dead in its tracks? On August 6, 2025, we found out. When the alert came from the Pan-STARRS survey, led by principal investigator Ken Chambers, the numbers were alarming. The interstellar object 3I Atlas was accelerating, its spectrum flashing with unexpected metals. There was no time for committees. In a move almost unheard of, a director's discretionary time override was triggered, sidelining Webb's entire multi-million-dollar schedule. This wasn't a normal target of opportunity, this was an emergency. The command chain went straight to the Space Telescope Science Institute director's desk, requiring unanimous approval. It was a massive risk. A single unscheduled slew of that magnitude can cost over 12 hours of precious observation time and risks thermal shock to the delicate mirror segments. This time is meticulously allocated to dozens of other research teams who have waited years for their shot. At 2:17 GMT, after a rapid 38-minute repointing maneuver, the command went live, the tension palpable in the Baltimore control room. Webb's instruments locked onto an object that was already beginning to rewrite cosmic chemistry. Fewer than 4 such overrides have happened in Webb's entire operational history. None for an interstellar object. Early activity beyond Jupiter's orbit. Here's the first red flag, that 3I Atlas was no ordinary comet. It woke up in the deep freeze. Most comets are quiet until they cross inside the solar system's frost line near Jupiter's orbit, roughly 5 astronomical units from the Sun. But 3I Atlas was already active at 6.8 AU, far out where the Sun is just way too weak to sublimate water ice. Ground-based telescopes, following up on alerts from observers like Karen Meech at the University of Hawaii, noted a persistent brightening of 0.3 magnitudes in just 48 hours. For an object this distant, that represents a massive increase in its gas and dust output. This sustained activity, producing a tenuous coma when the surface temperature was below 150 degrees Celsius, pointed to a body born in a place fundamentally different from our own solar system. Its engine had to be a hyper-volatile ice, something that turns to gas in the slightest warmth of the distant sun. The comet's tail grew at a pace that stunned the teams watching, driven by gases that simply shouldn't have been active so far out. It was the first clue that the chemistry of this visitor, as cometary expert Michael Mumma might put it, was deeply, profoundly wrong. The carbon dioxide anomaly. When Webb's near-infrared spectrograph delivered its first data packet, the anomaly was impossible to miss. The absorption band at 4.26 microns was breathtakingly strong. It's the classic textbook signature for CO2, and it utterly dominated the spectrum. The final analysis confirmed a carbon dioxide to water ratio of 8:1. That isn't just an anomaly, it's a statistical impossibility based on every comet we have ever studied. For context, even the most CO2-rich comets in our system barely reach a ratio of 0.3. The gas production rate was staggering, calculated at over 1.5 times 10 to the 28th molecules per second, an output comparable to what the great comet Hale-Bopp produced when it was much closer to the Sun. Every cross-check from Hubble and the Keck Observatory confirmed it. This isn't a calibration error, it's a message. As a planetary scientist like Stephanie Milam at NASA would argue, from a star system where the chemistry of planet formation was completely inverted. Such a system might have formed around a carbon star, creating a world where carbon dioxide, not water, is the dominant ice. Nickel without iron, an impossible chemistry. This is where the story goes from strange to deeply unsettling. As the team at the European Southern Observatory analyzed the high-resolution spectra, they found clear emission lines for atomic nickel at 3,415, 3,524, and 3,525 angstroms. But the real shocker was what was missing: iron. In every celestial body ever studied, nickel and iron are chemically inseparable, forged together in the hearts of dying stars and scattered in a cosmic ratio of about 1 part nickel to 15 parts iron. Yet, even with the Very Large Telescope's UVES instrument running at a resolving power of 80,000, iron was a ghost. The data was brutal. The upper limit on iron atoms meant nickel outnumbered it by more than 40 to 1. Spectroscopists like Neil Dello Russo at Johns Hopkins would confirm this is unprecedented. The only plausible, though exotic path is the molecule nickel carbonyl, which is so volatile it vaporizes at just 43 degrees Celsius. This molecule is extremely fragile and would break down under solar radiation, releasing the free nickel. But for that to be the explanation, the object had to form in a place that chemically isolates nickel on an industrial scale, a process unknown in nature. Trajectory anomalies and acceleration spikes. As if the chemical puzzle wasn't enough, the way 3I Atlas moved was just as bizarre. Davide Farnocchia's team at JPL, who are masters of celestial mechanics, flagged its trajectory before the Webb data even came down. The object wasn't just following the clean arc of gravity, it was accelerating. Over a 72-hour period, its velocity increased by nearly 0.12 meters per second squared, a non-gravitational push far beyond what the observed outgassing could explain. The thrust calculated from the gas production rate was an order of magnitude too low to account for the observed change in speed. The data also showed tiny sharp jumps of up to 1.5 meters per second, as if an internal force was flickering on and off, rather than a steady, continuous jet. This stands in stark contrast to Oumuamua's smooth acceleration. For an 11-kilometer-wide body with an estimated mass of over 1 trillion kilograms, this erratic push is like watching a mountain suddenly lurch forward with no visible cause. The physics just doesn't add up. The acceleration was real, and it wasn't coming from ice alone. The lighthouse effect, mechanical light curves. Every object in space tumbles, but 3I Atlas's light curve is anything but natural. Photometric data from NASA's TESS satellite revealed a periodic brightening that pulsed with the precision of a clock, sweeping like a lighthouse beam every 7.2 hours. A tumbling potato-shaped rock would produce a smooth, rolling sine wave of light. This was a square wave, ramping up in brightness by a full 1.8 magnitudes in just under an hour, holding steady, and then dropping off sharply. This implies an object with distinct flat sides and sharp edges, unlike the irregular shapes of natural bodies. Furthermore, outgassing should create torque, causing the object's spin period to change over time. Instead, the 7.2-hour period remained locked in to within 1,000th of a second, a major physical contradiction. An expert on exoplanet light curves like MIT's Sarah Seeger would immediately recognize this as unnatural. The sharp increase in brightness also hints at a highly reflective, possibly metallic surface being periodically revealed to our line of sight. Ancient sky metal, historical context. The idea of strange metal falling from the sky is really woven into our oldest histories. Around 3200 BCE, ancient Egyptians hammered beads from iron they couldn't have smelted. Discovered at Guernsey, analysis shows they are nearly 30% nickel, a cosmic fingerprint proving they were made from a meteorite. Centuries later, a dagger was buried with Tutankhamun around 1323 BCE. Its untarnished blade contains 11% nickel. The Egyptians called this material Baya en Pet, or iron from heaven, with a hieroglyph combining sky and metal. Further afield, the Inuit of Greenland used the Cape York meteorite for centuries as a source of iron for tools and harpoons. As historian Lydia Baum of Heidelberg University notes, these cultures knew this metal was not of the earth, it was a gift or a warning from the gods. This ancient reverence for rare, otherworldly materials, well, it mirrors the intense scientific focus on the anomalous metals being broadcast by 3I Atlas today. Avi Loeb's challenge to consensus. You can't have a conversation about interstellar anomalies without Harvard astrophysicist Avi Loeb. When the data on 3I Atlas came out, he immediately argued in a new preprint that these are all potential hallmarks of something engineered. In the lab, separating nickel from iron is done via the MON process, which eerily uses carbon monoxide to create volatile nickel carbonyl, the exact chemistry hinted at in the comet's coma. Loeb argues that while the community scrambles to invent exotic natural comets, we must apply Occam's razor. Is it simpler to invent new astrophysics? Or to consider an existing category of object we've theorized about, technology? His critics rightly say extraordinary claims require extraordinary evidence. But Loeb's position, now supported by his Galileo Project initiative, is that the evidence is already extraordinary. The project's mission is to actively search for technological signatures, and 3I Atlas fits the profile of exactly what they are looking for. Clinging to familiar explanations when the data screams otherwise is a failure of scientific imagination. Scientific community divided. The revelations about 3I Atlas have sent shockwaves through the astronomical community. On one side, scientists like Michelle Bannister of the University of Canterbury are pushing for natural explanations. They propose that 3I Atlas could have formed in a carbon-rich protoplanetary disk around a carbon star, where unique chemical conditions, while improbable, might allow for the formation of nickel carbonyls. It's a theory that pushes the boundaries of known astrophysics but keeps the object within the realm of the natural. On the other side, a growing number of researchers, emboldened by the sheer number of anomalies, are starting to take the artificial origin hypothesis seriously. They argue the combination of its 40-to-1 nickel-to-iron ratio and mechanical light curve is too much to be a coincidence. The debate is raging on preprint servers like ArcSiv, with some suggesting it could be a probe, a solar sail fragment, or even derelict industrial material from another civilization. This isn't an angry argument, but a rigorous process where every theory is being stress-tested against the hard data. NASA's High Anomaly Classification. Officially, NASA's Planetary Defense Coordination Office, under Lindley Johnson, has flagged 3I Atlas as a high-priority scientific object. While it poses no impact threat, its trajectory is being monitored by JPL's Sentry 2 system with an unusual condition code 9, indicating a trajectory so unpredictable it defies reliable long-term projection. This flag essentially tells the entire astronomical community that all bets are off for where this object will be in the future, making follow-up observations extremely difficult and urgent. Internally, this triggers discussions at the highest levels of NASA's Planetary Science Division about the fundamental nature of the object. It becomes a question not just of tracking, but of understanding. The tension between the cautious public statements and the urgent internal scramble to understand what they are dealing with is palpable. The official line is more data needed, but the unofficial reality is that this object is an enigma of the highest order. So, what is 3I Atlas? Is it a cosmic fluke, a messenger from a type of star system we've never imagined, with a chemistry that rewrites the rulebook? Or is it something more? Is this the first truly unambiguous sign that we are not alone in the universe, a piece of technology coasting through our solar system? The data is tantalizing, troubling, and refuses to give us an easy answer. For now, the truth hangs in the balance, waiting for the next round of observations to tip the scales one way or the other. What we do know is that this visitor from the dark has changed the conversation forever. Don't forget to like, subscribe, and hit the bell icon for more deep dives into the mysteries of our universe. What do you think 3I Atlas is? Let us know in the comments below. Thank you for watching Stellar Tech.